Good morning and welcome to the Minimum Good Design. This is the third webinar in the Building Smart program series. This series is brought to you jointly by DTE Energy and Consumers Energy. Consumers Energy is Michigan's largest energy provider. They provide natural gas and/or electricity across the entire Lower Peninsula to 6.8 million of the state's 10 million residents. Earlier this year, Consumers debuted its all-electric bucket truck. Now, Consumers already offers homeowners rebates for home EV charging through its Power Michigan Drive program. And with this new all-electric bucket truck using zero emissions energy, Consumers is taking yet another step in its commitment to powering Michigan's EV transformation. Earlier this month, just a couple of weeks ago, Consumers broke ground on the construction of its Blackman Solar Gardens project. Slated to start generating electricity by the end of the year, this new project will be Consumers' fourth solar installation. It will include nearly 5,000 solar panels and generate enough renewable electricity for approximately 2,500 future solar gardens customers. DTE Energy is also committed to giving Michigan a greener energy grid. Last year, DTE launched its largest solar park and battery energy storage center. It invested $4.4 billion in electric and gas infrastructure to improve reliability and generate cleaner energy. Through its energy efficiency programs, last year, DTE brought comfort to Michigan families with $63 million in energy efficiency assistance. And it supported vulnerable customers by connecting them to another $144 million in energy assistance. DTE is the state's largest electric utility with 2.3 million customers in Southeast Michigan, as well as 1.3 million natural gas customers across the state, including the Upper Peninsula. My name is Sonia Ponce, and I will be your speaker for today. We'll be talking about the minimum characteristics of good residential design. It bears mentioning that those minimal characteristics are rooted in our 2015 Michigan Energy Code that applies to single and multi-family residential buildings of 3 or fewer stories above grade. We'll start things off with a discussion of documentation. Then we'll look at the climate, load, and equipment characteristics and wind the discussion up with building systems. We'll look at the envelope, HVAC system, domestic hot water, lighting, and then we'll wrap up with home pools and spas. After watching this webinar, we hope you walk away with a greater comfort and confidence in your abilities to discuss the minimal elements of good residential design with homeowners and potential homeowners who are likely your customers, and that you feel more confident in your ability to apply residential best practices for air barrier installation. Now, before we get started, we're going to take a poll to see who's with us in the audience today. And while we're doing that, while John is pulling that information up, I'm going to share some fun facts with you about Consumers and DTE Energy. So this webinar series is not the first collaboration between the two utilities. One of their long-standing partnerships is the Ludington Pumped Storage Power Plant, which they co-own. It was completed in 1973, and the pumped storage plant is a hydropower facility that kind of acts like a giant battery. It stores energy by pumping water uphill to an elevated reservoir during periods of low demand, and then releasing that water through turbines to generate electricity during periods of high demand. Now, the reservoir can hold up to 27 billion gallons of water. That's nearly 41,000 Olympic-sized pools, or 900,000 average-sized in-ground backyard pools. The 6 reversible turbines can produce a combined total output of almost 1,900 megawatts. That's enough to power a community of 1.4 million people. Okay, so it looks like John has the results from our survey, and it looks like the category that most people fall into today is energy raters. So we have more energy raters than any other category of person. So welcome to the energy raters. And also welcome to the architects, the engineers, the home builders, the contractors, and the code officials that we have in the audience today. We hope you find this information valuable. So let's start with the general characteristics of a good design. First of all, it's going to pass the checks and tests that are going to be required by the code inspectors. It's going to meet the safety and health needs of the homeowner and occupants. Its systems and their operation and maintenance requirements will be well documented so owners can operate and take care of the equipment and systems over their product lifetimes. And the designs will have enough built-in flexibility so that if the homeowner wants to make changes to incorporate new technologies down the road, or if the home gets sold and the new owner wants to make upgrades, they can do it easily. Essentially, even though it's not a great design, a good design still checks a lot of boxes. Now, we'll talk about this more in detail later, but because of its significance to minimum criteria for a good design, and because it requires documentation, I'm going to introduce it here. The air barrier. The air barrier is vital to protecting buildings from air leaks and moisture infiltration. When it's installed correctly, they significantly enhance energy efficiency, moisture control, indoor air quality, thermal comfort, and structural durability. We measure building air leakage with a blower door. Now, the blower door consists of a frame and a flexible panel that fit into the doorway, a variable speed fan to develop the differential pressure, a digital pressure gauge to measure the difference in pressure from the inside to the outside of the home, and a manometer to measure airflow. The test is conducted by an independent third party, and the maximum allowable leakage rate for minimum good design is 4 air changes per hour at a differential pressure of 50 pascals. Once this test is completed and the results are satisfactory, a signed written report of test results is required to be provided to the code official. Other required documents include scaled drawings. These describe the construction details of the home, including its structure, duct ceiling, duct and pipe insulation, and location, as well as the size, type, and efficiency and quantity of equipment, which are all valuable for understanding how systems are going to be working together. Another key thing these drawings should include is a narrative of how the lighting controls function. Now, in the past, we're very used to having simple switches throughout the home, but today we see advanced controls typical of commercial spaces making their way into residential spaces. For example, we see timers, occupancy sensors, and even daylight sensors in homes. We want to make sure that homeowners understand how these controls are intended to work and how to program them. And we want to be sure this is explained to them, not in technical jargon, but in layman's terms that they will easily understand. Now, of course, the pièce de résistance is that the drawings should detail the continuous air barrier and the air sealing techniques. We'll dig deeper into this a bit later in the webinar. Although in general, I guess returning to documentation, although homeowners won't be installing systems and equipment, it's important to provide them with the manufacturer's installation instructions. This is valuable for them to understand how to properly and safely use, maintain, and troubleshoot the products that'll be in the home. This also will help to ensure product longevity and optimal performance. Now, these documents also contain important information on the manufacturer's product registration and warranty requirements. So if the homeowner has a warranty claim, particularly after the builder's warranty expires, if they have these important manuals, they will have instructions on how to process those claims. Insulation is one of the most important, if not the most important component of the home envelope system. A home that is well designed and well constructed will include a certificate of insulation with details on the type and manufacturer of the insulation product used. Additionally, where blown in insulation is used, it'll include information not just on the initial installed thickness and R value, but because that insulation is going to settle over time, it'll also provide a settled thickness, a settled R value, as well as the coverage area and the number of bags of insulation that were used to obtain that R value. So if the homeowner wants to increase the thermal resistance later on down the road from the existing R value to a higher R value, they can easily calculate how much and of what R value they need to add. Batt insulation comes with R values printed on the craft paper. But since no such paper exists for blown-in insulation, a good design will incorporate a marker to indicate the proper height of the insulation. The markers should be affixed to either trusses or joists. The markers should have numbers that are at least 1 inch high so that they're legible from the attic access. And the markers should be facing that attic access, so a person doesn't have to enter the attic space in order to read the marker. And because that blown-in insulation may not settle evenly across the attic floor, there should be multiple markers spaced out so that each one covers no more than 300 square feet. There should also be a performance certificate for the entire home. This should succinctly list all the key thermal and efficiency performance data for the major building systems, the home envelope elements, the insulation, the roof, walls, floors, windows, doors, as well as the HVAC and water heating system. And rather than handing this certificate to the homeowner in a closeout package, this certificate should be permanently affixed to the main electric distribution panel. That way, it doesn't get misplaced or lost if the home changes hands. It's readily conveyed to the new owner. And care should be taken so that this certificate doesn't obscure any other important information that may be on that panel, right? We don't want to cover up circuit names and things like that when we're affixing this to the electrical panel. And lastly, for documentation, most homeowners know that they should be inspecting furnace filters regularly and changing them out when necessary, but they may overlook the fact that the water heater requires annual maintenance too. Like the tank needs to be drained and flushed. The anode rod needs to be inspected. Flue pipes and vents need to be inspected for corrosion. The burner assembly needs to be cleaned. So a good design will include labels affixed to each piece of equipment with instructions for what regular maintenance tasks need to be performed and how frequently they should be performed. The label should include minor tasks that the homeowner can do themselves, as well as the major tasks that they may want to hire a maintenance service provider to do for them. Now, components like windows on the roof, which also require annual maintenance. For example, windows, the caulking around them needs to be inspected, any loose caulk needs to be removed, and the gaps need to be sealed up. But it would be impractical to include labels for components like these at the equipment, and nobody wants a bunch of labels around their, at every window around their house. And for the roof, there's not a way to attach a label such that it would not be impacted by weather, right? So maintenance instructions for these types of components should be included in a turnover package that's given to the owner when they get their keys to their new home. A good design will also take into consideration where the home is located. Now, Michigan has 3 distinct climate zones. These are defined by the number of heating degree days. Degree days are based on the assumption that when the outside temperature is 65 degrees Fahrenheit, we don't need heating or cooling to be comfortable inside. The heating degree days are actually the difference between the daily temperature mean and 65. So, so if the temperature mean is above 65, we subtract 65 from the mean, and the result is cooling degree days. If the temperature mean is below 65, we subtract that mean from 65, and the result is heating degree days. Now, without heating degree days, comparing energy use over two periods would be like calculating a car's miles per gallon without knowing how far you had actually driven. So if a homeowner wanted to know if, for example, the attic insulation that you added for them, right, that you installed for them, was actually saving them energy, you could help them by reviewing their energy bills to determine first how much energy was used before and after the upgrade. That'd be like the gallons in the miles per gallon. Um, then, using the heating degree days, you could determine how much relative heating would have been needed during those same periods before and after the upgrade. And that'd be like the miles. So instead of calculating miles per gallon, you would calculate CCF or MCF, 100 cubic feet or 1,000 cubic feet of natural gas per degree day, actually heating degree day, for each period. And then comparing the two would indicate whether the energy use had gone down. Now we can see here from the climate data shown that as we traverse the state, as we go up north, the heating degree days increase and the cooling degree days decrease. This means that if a home were built, for example, in Detroit, and a duplicate home with the same thermal properties were built in the Sault Ste. Marie house would require more heating and less cooling than the Detroit home. And of course, this tracks with what we know of Michigan climate, right? If you like winter sports, you go north in the winter, right? But climate zone isn't the only factor that determines how much heating and cooling energy a house will need. A good design is also based on a good, solid estimate of the home's internal heat gains and losses, which are based on things like how big the house is, the layout, whether it's all on one level or there are multiple stories. What are the quantities, sizes, and orientation of the windows and doors? On what side of the building are they? How many are on the southern exposure? What's the anticipated occupancy? How many bedrooms are there? What's the anticipated activities in the home? Is there a gym or a game room in the basement? How many appliances are there? What are the appliances? And what kind of ventilation system is there? How many air changes per hour are there? And how much outdoor air is being brought in that needs to be heated or cooled? Now, if we were talking about grandma's apple pie, bigger might be better. But when it comes to HVAC equipment, bigger is not necessarily better. A good design does not use HVAC equipment that is oversized, because oversized equipment often cannot modulate low enough to match the actual load. So that means that it's going to use more energy than necessary to meet the demand. And since it can't modulate down too well, larger equipment or oversized equipment often cycles on and off more frequently. This reduces its life expectancy. And also, larger equipment has a higher first cost, which is never good for the homeowner. So a good design uses properly sized equipment, right, to meet the anticipated load, and that equipment has the ability to modulate to closely match the load as it changes throughout the year and over the course of a day. Now, the load estimate and the equipment sizing are calculated in accordance with manuals J and S, respectively, from the Air Conditioning Contractors Association. Now, these manuals outline in detail the necessary data and the steps needed to accurately determine the home heating and cooling requirement and the appropriate equipment size to meet that requirement efficiently and economically. Floors can account for 25 to about 30% of the building envelope surface area. And when defects in the air barrier and insulation system exist, heat is lost through the floors over unconditioned basements and vented crawl spaces. This can cause cold floors, which we know are not comfortable, and it can increase heating and cooling costs. So a good design will make sure floor insulation is in full contact with the subfloor air barrier. The insulation will be installed in the floor joist bays without misalignment, without compression, without gaps or voids. And if necessary, there may be some supports like metal staves or netting to help keep that insulation in permanent contact with that air barrier above. And if there's a slab on grade, the slab edge will be insulated with insulation installed vertically or horizontally on either the inside or the outside of the foundation walls. If it's installed horizontally, it still has to cover that vertical edge, the vertical slab edge, and then extend horizontally either to the interior or the exterior of the home. If it extends to the exterior, it has to be protected by pavement or at least 10 inches of soil. Now, the minimum distance that it has to extend beyond the slab is determined by climate zone. In Southeast Michigan, it has to extend at least 2 feet. But in climate zones 6A and 7, the minimum distance that it has to extend is 4 feet. There are also unique thermal requirements when there's a basement and 50% or more of the wall assembly is below grade. This table is showing the wall U factors, which are the inverse of R values, where R values pertain to a single component of the wall. For example, just the brick or just the insulation. The U factor actually pertains to the entire wall assembly. And instead of being a thermal resistance, it's a thermal conductance, or a measure of the rate at which heat is allowed to penetrate the assembly. Now, these two are based on climate zone. In Michigan's northernmost climate zone 7, the basement wall assembly U factor is about 8% lower than it is in Southeast Michigan, meaning that a good design for a home located in climate zone 7 requires a slower rate of heat loss than a similar home located in climate zone 5A or 6A. In order to get that slower rate of heat loss, we need more insulation. Now, for conditioned basements, the wall insulation should go from the top of the basement wall down to 10 feet below grade or to the basement floor, whichever is less. For unconditioned basements, a good design may also insulate the basement wall, or it may instead have insulation applied to the floor above, which would be the unfinished ceiling basement. Now, instead of a basement, some Michigan homes have crawl spaces, which can be vented or unvented. Vented crawl spaces, which are open to the elements, should be uninsulated and have at least one opening within 3 feet of each corner of the crawl space. The net size of those openings should either be 1 square foot for every 100 square feet of crawl space area without a class 1 vapor barrier, or 1 square foot for every 1,500 square feet of crawl space with a class 1 vapor barrier on the ground. Now, alternately, right, the crawl space can be unvented or closed. These crawl spaces have sealed rim joists and walls underneath the home. The walls and the rim joists are sealed from the outside environment. So the crawl space is essentially an extension of the home's conditioned space and keeps the water lines and water heaters and mechanical equipment, whatever else may be down there, in conditioned air. This is nice from an energy perspective because then the utilities aren't exposed to the extreme winter cold. Now, in unvented crawl spaces, the energy code requires that the crawl space wall insulation be permanently fastened to the wall and extend all the way from the floor above down to the finished grade level. And then after that, extend another 2 feet, either vertically or horizontally, or a combination of the two. It requires that the crawl space floor, really, which is the exposed earth, must be covered with a class 1 vapor retarder, like a 6 mil poly. And the joints of that vapor retarder have to overlap by at least 6 inches and then be sealed or taped. And not done yet. And the edges of that vapor retarder need to extend at least 6 inches up the stem wall and be attached to the wall, permanently attached, permanently fastened to the wall. Now, unvented crawl spaces are actually ventilated. Their ventilation rate is at 1 CFM for every 50 square feet of crawl space area. And that ventilation can either be by mechanical exhaust or it could be by a supply of conditioned air actually from the home. Now, for above grade walls, the assembly U factor for wood frame walls is the same across the state. It doesn't matter where you are. But for mass walls, it does vary. And of course, it varies based on climate zone. Now, mass walls are walls that have a capacity of at least 6 BTUs per square foot per degree temperature differential, Fahrenheit. So these are constructed of materials like concrete block, masonry cavity, brick, and solid timber. Those are the ones that we typically see in Michigan. There are other materials that could be used: adobe, compressed earth block, rammed earth. These are much more rare, though, in Michigan. But a good design will take the wall construction material into consideration. Additionally, a well-constructed home will also ensure that any insulation in that wall is not compressed behind the wiring or plumbing, because this reduces the wall, the R value of the insulation, right? A well-constructed design will also make sure that the insulation is filled the entire cavity and that any batt insulation is cut to fit and leaves no voids. Now, roofs represent either, roof R values are either for the cavity insulation or for the sheathing. For homes with attics, the insulation has to be installed to allow for free circulation of air through the attic eave vents. Now, the use of a standard truss system can cause cold corners and also can contribute to the formation of ice dams, which we are prone to here in Michigan, right? This is where you've got heat from the house, it melts the snow on the corner of the roof, which then runs down into the eave where it refreezes and builds up a dam that can push water back up underneath the shingles. Now, this happens in part because when blowing insulation into a standard roof truss system, because of the slope of the truss, the insulation tapers as it reaches the exterior wall plate. Now, the R values listed in column 1 here, which come from the prescriptive building envelope criteria, assume this standard truss system. But if the insulation is allowed to be installed with no taper at full height over the entire floor out to the exterior wall plate, a reduced insulation R value is allowable. And that's what's shown here in column 2. So for example, if the requirement is for R38 with a standard truss, R30 can be used if a raised heel truss is used. That'll give you full insulation thickness all the way out to the exterior wall plate. Now, sometimes there may not be sufficient space between the truss and the ceiling below, right? So for example, if you have a vaulted ceiling, which we do have here in Michigan as well, and there may not be space to include the thickness necessary to achieve a certain R value. In those cases, a reduced R value is acceptable as well. So for example, if you had a vaulted ceiling with a requirement for R38, but there's no space, there's insufficient space to add the thickness required to get R38, R30 is acceptable. The design can be deemed to meet the energy code with the R30 as long as that R30 covers no more than 500 square feet or 20% of the total insulated ceiling area, whichever is less. Now, whenever air permeable insulation is installed in vented attics, a baffle also has to be installed. The dark pink at the underside of the roof sheathing in this image here is a good representation of an eaves baffle. Now, the baffle's purpose is twofold. First, it directs air through the vents, up and over the insulation. Second, it helps to ensure proper ventilation by preventing the insulation from falling back and blocking the vents. Now, it can be made of any solid material that you like, as long as it's adjacent to the soffit and eave vents and maintains an open area, at least the size of the vent. Now, some say baffles should extend at least 2 inches, 2 feet, 1 inch, a foot and a half beyond the insulation. But really, there's no minimum requirement for how far it should extend beyond the insulation. It just needs to extend far enough to create that channel for unrestricted airflow. The bottom of the baffle should start at the outer edge of the exterior wall top plate so that it allows for maximal insulation coverage there. The baffle should be continuous even if the soffit venting is not. Right? This helps to ensure that no ventilation air bypasses the baffle. We also want to make sure to seal the bottom edges of the baffle to the top plate in order, again, to prevent any air from bypassing and also to prevent air from leaking into the insulation. Now, in a good design, attic doors and hatches will be weather stripped and insulated. The R value of the insulation will be the same as the R value of the surrounding surfaces. So, for example, if the ceiling is insulated to R38, then the access hatch will also be insulated to R38. If the ceiling is insulated to R49, the access hatch will also be insulated to R49. That hatch or door will also have a baffle to prevent the insulation from falling out when the hatch or door is opened. And if there's any equipment that may need servicing, there will be a clear path to it. And that path will be such that no insulation is damaged, stepped on, or compressed in our getting to that equipment. A good design will also use quality fenestration products that are labeled with their energy performance as tested and affirmed by the National Fenestration Rating Council. Now, the NRFC has independent labs that test doors, windows, and skylights for their thermal performance. This includes the assembly U factor, but it also includes visible transmittance, how much visible light energy passes through the glazing material. It includes solar heat gain coefficients, how much solar heat passes through the assembly, and it includes air leakage. Now, if the fenestration products are not labeled, then default energy performance factors are assigned to them and used for calculation purposes. For example, a labeled double pane low E window or a spectrally selective window might have a U factor of 0.29. I recently installed windows in my house. They have a U factor of 0.29. But if that same window was not NRFC labeled, it would be assigned a U factor between 0.55 and 0.80, depending on the framing material. Now that's 90 to 175% higher in U value. That represents a significant energy performance penalty. It also represents a cost penalty. So again, a good design uses NRFC labeled fenestration products. And those products meet the performance criteria based on the climate zone in which they're going to be located, not only for thermal conduction, but also for air leakage, solar gain, and visible light transmission for anything that has glazing. And for the U factors in particular, there are maximum factors for the base fenestration assembly, and there are calculated maximum area weighted average factors that can be used in a trade-off approach to compliance. Whichever approach is used is the designer's choice. It's their prerogative. Now that we've talked about envelope insulation, which slows down the rate of heat transfer through the walls, roofs, and floors, let's talk about the air barrier, which seals up the structure and minimizes unwanted air infiltration and exfiltration, which can increase the amount of air that must be conditioned, heated, or cooled to maintain comfort in the home. So, a good home builder will ensure that her or his staff is well trained in proper sealing techniques and in how to identify good and bad or incomplete seals. A home with proper air sealing, or a home with poor air sealing, a home with improper air sealing will not pass a code inspector's envelope check. All right, so this is going to require rework, which would be an additional cost that the design and or construction team would have to eat. And nobody wants that, right? Nobody wants that. So a good design will have the air barrier located properly in the ceilings, walls, and floors. And there will be air sealing between attached garages and conditioned spaces. A good design will have specified and visibly shown on the drawings a continuous air barrier. And it will be specified that all breaks and joints in the thermal envelope are to be sealed. So for example, in attics, a good design will ensure that joints between the attic floor and the top of interior walls are sealed. It will ensure that the access doors and hatches are sealed. And it will ensure that the insulation is aligned or in substantial contact with that air barrier. Corners and headers are to be insulated, and then the junction of the foundation and the seal plate are to be sealed. Joints where two walls meet are to be sealed. Where walls meet ceilings and where walls meet floors are to be sealed. And knee walls are to be sealed. Places where fenestration products penetrate the air barrier, like around window frames, these will be sealed with a continuous bead of caulk. Right? When caulking, the caulk gun should be placed at a 45-degree angle, and care should be taken to ensure that the caulk adheres to both sides of the seam, right? Both the top and the bottom. And if necessary, before it dries, smooth the caulk not with a finger, but with a putty knife. The space between the window and door jambs and the framing should also be sealed, as should the space between skylights and their framing. And for moving parts like casement windows, for example, and sliding doors, weather stripping should be used to seal gaps where the window or the door meet the frame. This will help ensure that the permissible assembly leakage rate is not exceeded, right? Because that leakage rate is something that comes from the factory, and they're assuming that their product is installed properly. So if it's not installed properly, the leakage rate may be in excess of what's printed, what's labeled on the product. At floors, a good design will include caulk or foam to be used between the rim board and the sill plate, between the rim board and the subfloor, and at all seams, gaps, and holes or penetrations in that subfloor. And at rim joists, wherever they form the thermal boundary, they should be insulated and sealed. The insulation should be individually cut for each joist bay. We should not assume that because the floor joists are evenly spaced that each joist bay will be exactly the same. Those wood members differ, right? And so each bay will be a little bit different. It could have piping or conduit or wiring running through it as well. So each bay needs to be looked at individually, and insulation needs to be matched to it individually. Now, in lieu of rigid insulation, spray foam can also be used at the rim joist. If foam insulation, whether it's spray or rigid board, is more than 3¼ inches thick, or if the space is going to be permanently habitable, insulation needs to be covered by a thermal barrier such as gypboard. But a good design will specify that all penetrations greater than 1/4 inch are filled with some sort of steel wool or backing or other pest-proof material before the sealing takes place. We don't want any bugs, we don't want any critters. A good design will also use caulk or foam to seal the insulation and thermal barrier in the joist bays. And a good design will, very importantly here, specify that all the applicable sections of that house-wide insulation certificate that we talked about earlier, we'll make sure that that gets filled out with this information about this basement insulation as well. So it will include the coverage area, the thickness, and the R value of basement insulation. A good installation will use caulk and spray foam to seal gaps around wiring, piping, and venting. It'll ensure that there are cut pieces of rigid foam or plywood that are then caulked in place to block larger air gaps. And it'll use caulk or putty to seal around electrical boxes, or will instead use boxes with built-in rubber gaskets. Now, whether they are shielded or not, all recessed lighting fixtures installed in the thermal envelope should be rated for contact with insulation. So they should be IC rated. They should also have an air leakage rate of less than 2 CFM at 75 pascals. And a good design and construction team will ensure that there is either gasketing or, better yet, a continuous bead of caulk between the fixture housing and the ceiling drywall. For perimeter walls with plumbing, a good design will ensure that the air barrier is installed and sealed between the exterior wall and the tub or the shower. It'll use caulk or spray foam, or again, pieces of rigid blocking material to close up any gaps around the piping. And if there are any electrical outlets on that perimeter wall, as mentioned previously, caulk or putty would be used to seal around them, or gaskets would be used. Similar to recessed lighting housings, a good design will ensure that the HVAC register boots, whether they're for supply or return, are sealed. If they're in the wall, they're sealed to the drywall. If they're in the floor, they're sealed to that subfloor. And for homes with wood-burning fireplaces, a good design will incorporate things like glass doors, tight-fitting flue dampers, as well as sheet metal and fire-rated caulk to seal around the flues. A good design will also draw combustion air from outside rather than inside the home. Because if we draw it from the inside, we can increase the release of byproducts of combustion or incomplete combustion, carbon monoxide. We release those into the home, and that significantly reduces our indoor air quality. It reduces our ability to enjoy the home. Now let's take a look at the HVAC system components. When they're installed in the building, when ductwork in particular is installed in the building but outside the conditioned space, ductwork in a good design will be insulated to at least R6. If the ductwork is not just outside the conditioned space, but also outside the thermal envelope, it'll need to have a higher R value of at least R8, which provides about 33% more thermal resistance. And all the duct joints and seams, both transverse and longitudinal, will be sealed either by welding or with approved methods like mastics or liquid sealants or UL listed tapes. What won't be used to seal ducts is duct tape. Fun fact here, duct tape was originally known as duck, D-U-C-K tape, because it was made from a heavy cotton cloth that was called duck cloth. Now, this cloth was water resistant, so naturally its performance was likened to how water rolls off a duck's back. It was developed in the early 1940s by a Miss Vesta Oral Stout. It was developed for military purposes. But when soldiers came home from World War II, they brought this tape with them, and eventually it found a new application in the housing market for connecting HVAC ducts. And as this became the predominant use for the tape, the name shifted from DUCT tape to DUCK. I'm sorry, from DUCK tape to DUCT tape. And the standard color of the tape was changed from military green to silver gray so that it could match the ductwork. But over the years, field reports and research, particularly some research coming out of Lawrence Berkeley National Labs, began to reveal that this tape really wasn't all that reliable for ductwork, particularly under temperature variations because it could become brittle, could simply fail, or even catch fire. So when the IRC, the International Residential Code, was developed in 2000, it prohibited its use for sealing ducts. Now, it doesn't do that directly. It doesn't say that you can't use duct tape. What it does say is that any tape that's used has to be UL listed. UL 181A for fiberglass duct and UL 181B for flex duct. And since duct tape doesn't bear those UL labels, it can't be used for sealing ducts. But after that ductwork is properly sealed using UL listed tapes if necessary, similar to the whole house, it too gets leak tested. Now, this is a requirement when the ductwork and the air handler or forced air furnace or what have you are outside the home's thermal envelope. If they're entirely within the home's thermal envelope, this is not required, but it's still a good idea. Now, duct leakage testing can take place either after all the construction is done, or it can take place at rough-in, either before or after the furnace is installed. Now, if the furnace is in place, the maximum allowed leakage rate is 4 CFM at 25 pascals or a tenth of an inch. If the furnace is not yet installed, the maximum allowed leakage rate is lower. It's 3 CFM, still at 25 pascals. Additionally, the furnace itself or the air handling device must have a manufacturer's listed cabinet air leakage rate no greater than 2% of its design airflow. And any HVAC piping in a good design will be covered with insulation, particularly if it's conveying fluids that are at elevated temperatures of 104 degrees or higher, or if it's at temperatures that are depressed at less than 55 degrees. The R value for that insulation, the requirement, the minimum requirement, is R3. Now, in the past, many homes were ventilated manually, mostly by opening windows, but also the opening and closing of doors. Some older homes in Michigan, like mine, have manually operated kitchen exhaust fans. But today, for IAQ purposes, well-designed homes require greater ventilation. And this can either be for the entire house or it can be local to specific rooms where pollutants are likely to be generated. The exhaust air flow rate depends on whether the exhaust is continuous 24/7 or if it's intermittent and only used when needed. For example, local kitchen exhaust that operates 24/7 would be at a low ventilation rate of 25 cubic feet per minute. But if the range hood fan were only to operate when cooking is taking place, then the airflow rate would need to be higher, 100 cubic feet per minute. But again, only when operating. Instead of local exhaust, We can also ventilate the entire house. Now, there are four approaches to this. We can use exhaust only, which, like local exhaust, removes air, but instead of just removing it from the kitchen or the bathroom, it removes it from the entire house. We can do supply only, which brings outdoor air into the home, and that can either be connected through the central air system, or it could have independent ducts, right? It could have its own ducts. We could do a combined system that does supply and exhaust. We call these balanced ventilation systems. They balance the air pressure in the house by bringing in and removing equal amounts of air. And then we have balanced ventilation with recovery, right, which can either be heat or energy recovery. So in addition to exhausting and bringing in air, these also extract sensible and latent energy from the exhaust airstream and use it to precondition the supply airstream, thus reducing how much the central system has to work in order to condition it, in order to condition that air. Now, regardless of which type of whole house ventilation system is used, for single and two family houses, as well as multi-family buildings with no more than 3 stories above grade, the minimum continuous whole house ventilation rate is based on the conditioned floor area and the number of bedrooms. Now, as with local exhaust systems, when the whole house system operates intermittently, they have to provide higher ventilation rates to compensate for the reduced operating hours. So for every 4-hour period, an intermittently operating system has to provide the same ventilation rate as what would be provided under a continuous operating system. So for example, if the system were to run at only 25% of the time, then the intermittent ventilation rate would have to be 4 times the continuous rate. If the system were only to run 75% of the time, then the intermittent ventilation rate would have to be 1.3 times the continuous rate. Additionally, a good design will specify and ensure that the ventilation fans used are energy efficient and that they have performance labels indicating that they meet the minimum efficacy requirements that the code inspector is going to be looking for. Now, excuse me, for reduced energy with forced air systems, a good design will incorporate a programmable thermostat that's capable of having different temperature set points at different times of the day, and that can have heating setbacks and cooling setups for periods when full heating or full cooling are not required. For example, at night when people are in bed under the covers, or when they're not home for hours at a time, as when they go to work, or for extended periods, as when they're like on vacation. The interior design conditions for a good design are 72 degrees Fahrenheit for heating and 75 degrees for cooling. But to encourage reduced energy use, the initial thermostat set points at turnover should be 70 degrees for heating and 78 degrees for cooling. And if the system includes a heat pump that has supplemental electric heat, the controls should ensure that that electric heat only comes on when the compressor system is not able to provide enough heat to meet the demand. And this can be located in the thermostat, or more than likely it's going to be integral to the heat pump itself. But either way, we want to be sure that we're only engaging electric heat when it's absolutely necessary. Now, in the past, heat pump technology was not that effective here in cold climates like ours here in Michigan. But today, there are specially designed low temperature heat pumps that can efficiently provide heating in heat pump mode all the way down to about 5 degrees Fahrenheit. So we want to make sure that when we're applying heat pump technology, that we're applying those low temperature heat pumps designed for our climate, and we want to make sure that they have a controller either at the thermostat or an integral control that only brings on that electric supplemental heat, which is far less efficient than heat pump heat. We want to make sure that we're only engaging that when it's absolutely necessary. Similar to HVAC piping systems, domestic hot water system piping in a good design will also be insulated, and it will also have an R value of at least 3. Now, this criterion applies, for example, when the piping is outside the conditioned space, when it's under a slab, when it's larger diameter, so when it's 3 inches or greater in diameter, as you might see in a larger home or in a multifamily situation. This is also required if the system is serving a continuously circulating recirculation system. But if that recirculation system is a demand-based system, meaning it only operates when it's necessary, then the domestic hot water piping only needs to be insulated to R2. For permanently installed lighting, typically we're talking about just the ceiling lighting fixtures. A good design will incorporate a high percentage, 75% or more, of high efficacy lamps. Now, these are lamps that have either 50 lumens per watt if they're between 15 and 40 watts, or if they're greater than 40 watts, they will have an efficacy of 60 lumens per watt. And this would not have been possible with older incandescent technology, but LED lamps, which use 25% of the energy of an incandescent bulb, with them, this is very doable. So the requirement is that either 3 out of every 4 bulbs in each fixture needs to use high efficacy lamps, or 3 out of every 4 fixtures needs to only use high efficacy lamps. Although technically the first option is available, it's really not likely that one would intentionally mix lamp types in a single fixture. So most good designs are going to have high efficacy lamps in 3 out of every 4 fixtures, if not all fixtures. For homes with heated in-ground pools and spas, unless the heater is using a heat pump or a solar energy source, there should be a vapor retardant cover for the pool or spa to reduce heat losses to the cooler air or loss of conditioned water through evaporation. And the heater should have a readily accessible on-off switch that does not require one to adjust the thermostat setting in order to turn the unit off. In other words, the on-off switch cannot be a knob that goes from 0 heat to heat level 10. Also, on that on-off control, it needs to be programmable and needs to have a schedule, and it needs to include the pump. And lastly, for pools and spas, if that pool or spa has a gas heater, if it's gas fired, it must not have a standing pilot. Now, those are the minimal elements of a good residential design. Let's do a quick recap. A good residential design is designed for the correct climate zone. A good residential design is well documented with certified energy performance characteristics for the major systems and envelope components, and this certificate is posted on the electrical distribution panel. A good design provides required documentation like scaled drawings and air leakage test results to the building official. It uses products that are tested by independent labs and bear manufacturers' performance labels for things like air leakage, thermal performance, and solar heat gain. A good design is properly insulated to the proper level, and a good design is thoroughly and properly air sealed at all junctions, joints, and penetrations, including around windows and door framing, at rim joists, at utility penetrations, and where recessed lighting penetrates the thermal envelope. A good design uses properly sized equipment for HVAC and domestic hot water. It uses equipment with programmable controls that are programmed. A good design meets the code criteria for the whole house air leakage rate, and it provides for mechanical ventilation for good indoor air quality. And last but certainly not least, a good design passes all the code inspector's checks. Now that concludes our session for today, unless there are any questions. And while we're waiting to see if there are any questions, we'll talk a little bit about the upcoming sessions. So this is my last session for a while. Your trainer for next week and for the next few weeks will be Chris McTaggart. Chris is a co-principal and technical director for Building Efficiency Resources. And for the past 15 years, he has served the residential energy efficiency industry as a curriculum specialist and quality assurance manager focused on home energy rating system, or the HERS system. Needless to say, Chris is a really great guy and an excellent trainer. I'm sure you will enjoy him over the next several weeks. His first session will provide an overview of above code programs. That'll take place next Tuesday at 11 a.m. I understand that there are no questions, so thank you very much for joining us today. We hope you found this presentation informative, and we look forward to seeing you next week. In the meantime, have a great holiday weekend.